All right, welcome everyone. In this video, what we're going to look at is the PEB structure, the process environment block, which is part of the one of the first videos I'm gonna create that covers some of the Windows internals. Now, there's a couple of primary reasons that I wanted to put this video together. The first is that we'll discuss it more. I'm going to kind of tie together some of the previous videos here. If you look for in the portable executable or the PE file playlist, you'll see kind of a progression of working to the export table. So we're going to talk about how walking the PEB structure can allow then to identify PE files in memory, particularly libraries, and then walk those export tables in order to resolve functionality. And you'll see this in a lot of malware and shell code in order to reconstruct an import table. The other thing then is to establish a baseline with the PEB, because so that there are other techniques here, other things that use the PEB structure, some anti-analysis that I'm going to cover in a later video. Okay, so one of the first things to take note of is that while this structure is documented on MSDN, it's fairly incomplete, although there are some important structures here that are documented. So you'll find that, for example, there's a byte value early in the structure for being debugged. That's one of those anti-analysis members that we'll talk about later, and simply that if a debugger is attached, then this will be true. So it's something that malware can check for, and anything that wants to look for a debugger. A lot of these are going to be reserved, though, and so what that's saying is if you look down, see the first member is reserved, you'll see it's reserved for internal use by the operating system. Now, fortunately, the symbols are defined there. These structures are defined in header files as well as imported into WinDbg. So I like to use WinDbg to explore that, because what we'll do is we'll not only look at those structures with an actual process, but then some code that is the foundation for walking the PEB to get the base address of a DLL in memory. So here you can see some code, simple program that has some inline assembly, and we'll go through all of these instructions. That'll be the last half of this video. Okay, as far as today's setup, I'm using WinDbg Preview. I've changed the theme to dark. I didn't know you could do that, so I did that for this video because it's just easier on my eyes, and adjusted the windows to maximize the command window. So that's where we're going to spend most of our time here to get started. Now, WinDbg has a command exclamation PEB, and what this will provide is more or less a summary view of the PEB structure, particularly where it's located in memory, as well as some of the like a summary of some of the important members that surround the PEB. Now, if we want to just look at the structure itself, we can use the dt command _peb for the symbol, and that'll give us a nice layout, the structure definition. So that'll be all the members with all their names, as well as the offset. So we can derive the size of that member if it isn't defined off to the right-hand side. So that can be very helpful. However, if we go back to the first command, and I apologize, there's going to be a lot of scrolling today just due to the amount of data that these initial structures have. You'll notice that this one appears to be a hyperlink, and that is absolutely the case. So we can click on that. In fact, any of these that are that are blue more or less serve as a hyperlink. You'll see there's a couple of things worth pointing out. Clicking on that link, use the dt command with our symbol, and then also provided the address. So by providing the address to these structures, what we get is not only do we have a breakdown of that structure and those members, but then we get all of the actual values mapped into it via this memory address. So basically all we're saying is, hey, WinDbg, go to this address and map whatever data is there to this structure, and that's what it's displaying. And we're going to use this a number of times through this demo. Okay, so that's the very, very basics with the PEB and where you find it. Now, one thing, if we go and just take a quick peek over at this code, FS30 hex is also going to be the where you're going to find the PEB. And so oftentimes for code that is going to utilize the PEB structure, you'll either see a direct reference to FS and then an offset of 30 hex, or you might see some math to try to break up and make it look not quite so obvious that it's trying to reference the PEB, but that's usually the first step. So if you see an instruction like this, then likely it is either part of the, resolving functionality via the method we're going to talk about, or possibly looking at some of those other structure members in order to do some anti-analysis. At least that's the two most common use cases that I've come across. Focusing back then on importing functionality. The structure that is located at an offset of +C hex is the PEB loader data, or PEB_LDR_data structure. Again, we can click on that, and that'll provide us with a breakdown of that particular structure. I do believe if we go back to MSDN, as I said, this is one of the few members here that are documented, although if you look at the definition provided, it's rather incomplete, especially compared to what we see here. So this has a number of members here, but the three most important, at least again in terms of this discussion today, is the in-load order module list, the in-memory order module list, and the in-initialization order module list. Now, these three members, you can see by the offsets, there's 8 bytes in between. These are a list entry item. And if we click on, let's say, that first one, you'll see that a list entry item structure is simply a forward link and a backward link. So these are the heads of a doubly linked list, with the forward link pointing to the forward structure and then the backward link pointing to the backward structure. Now, these three members here, they define or they provide access to, if we go back to our PEB loader data structure definition here on MSDN, you'll see that there is a LDR data table entry structure that defines what those forward links, backward links point to. So this structure right here, and I'm going to copy that, because then what we can do is we can just look at the structure in WinDbg. Of course, we could look at it on MSDN as we were doing. Now, you'll see, of course, quite a few different members here, but only a handful of things I want to point out and focus on, and again, in that context of resolving functionality. The first is the DLL base. Right, so what the DLL base represents then is the base address of that DLL in memory. So if we're trying to find a DLL, kernel 32, NTDLL, and then from the base be able to walk the export table, then this allows us to do that. We don't really need the entry point, but we could also use the full DLL name or the base DLL name. Let's say, for example, that you have code that is looking for a specific DLL. Well, then it can navigate to find, it can walk through this doubly linked list, getting the name of the DLL, comparing that, and then once it's determined or found the DLL that it's after, then get the DLL base name. Okay, if we go back, and I'm just going to make sure I did this right. So we're at our PEB loader data structure, right? So we're one structure off from the PEB. If we select the in order module list, because we're navigating the structure in memory, then what this value here is telling us is that is the base for that next structure. Right? So if we go back in history just a little bit, we can see, run that command, and what we should find is that at that address mapping that structure, we have these values. So our DLL base in memory is at F90000. We can do an LM command to confirm that. That is a true statement. We have, as you probably saw briefly, the path that the DLL was loaded from. In this case, it's our executable, and then just the base name. So, demo peb.exe, NTDLL.dll, kernel32.dll. Right, so that's it. With just a few instructions, as you'll see in that sample program, you can get to the base of a DLL. Now, you probably, if you're trying to import functionality, you probably don't need a pointer to yourself. But if we go back, okay, again, PEB loader data, so one structure off from the PEB, we have the in initialization order module list. And these three, why there's three lists is because, as the name implies, the structure, the sequence of DLL entries in the doubly linked list will vary depending on the list that you're looking at. So in initialization order module list, which is located here, this will be let's see, we get a memory read error at address and no string. So what happened, right? Well, we have the forward link, and that says that it pointed to this location. But what you have to keep in mind is that each one of these, again, I apologize for all the scrolling, but each one of these entries from the PEB loader data structure is pointing to a forward link or a backward link in that structure that we're investigating. That means that this points to forward link, backward link, the first 8 bytes in that structure. This begins at an offset of 8 bytes, so it'll be 8 to C bytes. This will then be the next offset. And you'll see that, if we go back to the structure that we just mapped incorrectly, you'll see here it is, right? Here's our list entry item. So here's the forward link and the backward link for the in-load order links doubly linked list. At an offset of 8, it's the in-memory list entry item, forward link, backward link. Okay, you probably get the point. So in order to map that correctly, we have to take into account where we're at in that structure. So if we're coming from the initialization order links, in order to get to the base of the structure, we'd have to subtract 10 because that's the offset that we're at. Now when we run that command, you'll see everything lines up, right? There's our Windows System 32 NTDLL.dll and our base name, as well as the DLL base, and I'll just have to assume that everything else matches up nicely. Okay, so very similarly, if we were to follow the forward link from the in-memory order links, this is at an offset of 8, we'd have to subtract 8 from it. All right, so just keep that in mind as you're either writing code or analyzing code, depending on this structure right here, depending on which one of these it's coming from, you'll have to adjust that offset once you get to this LDR data table entry structure. Okay, one other thing I wanted to point out while we're here is just the, actually accessing these different the path of the base name. You can see these are Unicode string structures. So let's pick on the base name. If we select that, that structure it's not simply just a pointer to the string. It actually contains a 2-byte value for the length and a 2-byte value for the maximum length, and then at an offset of 4, the buffer. So in order to get the actual name and ignore that leading 4 bytes, what you'll need to do is, let's just basically take this calculation again. That'll get us to the base of the structure. And then if we add 2C, that takes us to the base, that member. And then we add 4 more, then that'll take us to, that should display, and I'm using a DD to dump D words, that should display the pointer, which now if we print that out, you'll see it's NTDLL.dll. Right, so like I know the first time that I ever looked at the PEB structure, I can still remember the confusion I had, because once I figured out that I was at the base of this structure, calculated for whichever forward link got me here, then the offset didn't match up with any of this member alignment, and that's because we had to skip the first 4 bytes in order to get the DLL name. Okay, so that's how you can navigate. You can look at these structures in WinDbg. You can navigate them. You can actually map them to memory to see the raw value. If we go back to our sample program, then that's all that this code is doing. So we move into EBX, the pointer to the PEB. You can ignore this if you want. I just left it there in case you wanted to see. I'm just leaving it here in case you want to see, if you want to print the addresses as you go. Of course, we're going to step through this with a debugger, so we can just watch the different registers as we step through them. This gets the PEB loader and LDR data structure, as we discussed, moves that into EBX because they're not, that member contains a pointer to the next structure. So we don't have to add to the image base or anything. It's not an RVA. From there, this is getting the initialization order module list. That's at an offset of 1C. So if we look at the code, well, we'll step through it, I guess. And then finally, adjusting for the forward link offset, adding an offset of +8, moving that into EBX, storing that into this D word that was defined up above. And then down below, all I do is print, so use load library to get NTDLL, and this is just a handle to that. Compare those two, print them to compare them, right? And again, we could have all done that in a debugger, but now we have output here. So let's readjust the WinDbg here. I put this program into IDA just so I could figure out where I wanted to set my breakpoint. So IDA disassembles it for me, of course, and navigates us to main, right? And so I want to start here with the PEB structure. First things first, though, got to remember where we're at in memory. So breakpoint at F9101E. Now we can move to, there it is. I'll pin my step instructions. So move into EBX, EBX2ED000. And if we do bang PEB, now there's a little bit more crowdedness down here, but there's our PEB, 2ED000. Pushing EBX, that's just storing it so that I can call printf and then restoring it. So there's a push EBX and then another push, that's just to get the value for the format specifier. That add ESP8, so we've got the value that I want to print and then the format specifier string. So then that recovers from that, and then that restores EBX, because who knows what happens to EBX inside my call to printf. And then we're just moving into EBX. So here's our PEB loader data structure. So we could say, and the value of EBX, I'm not going to type that, so I'll just copy it. Oop. There we go. And you'll notice, okay, so I said we're going to move into EBX with this instruction, an offset of 1C. So that's this structure right here. So what we should see in EBX next is 603280. And there it is, 603280. We move into EBX, EBX plus 8. And again, if we wanted to just kind of verify, I don't think I need that. And if we want to verify, we can define our structure and our address. And I'll just scroll up here until we find okay, scroll up here, you'll see again, we've got the memory read errors, but keep in mind that this is where I'm at. So if I wanted to adjust that, I would subtract 10 hex. Okay, there we go. Right, and there we go. So now we can see. I mean, just looking at the names here is a quick way of telling. But again, we came in at this location on that offset, that member of that structure, and now this code is just moving from that location plus 8. Right. Well, 18 minus 10 to get the DLL base. That's the 8. So 77350000. We move that into EBX. You can see over here on the right that is in fact the address. And then the rest of it is just simply the load library and the comparison. So there is our PEB print, and there's the comparison between the two. So basically same thing. Okay, that's it. That's the PEB, at least an introduction to it if you're not familiar with it. How it's oftentimes used to locate DLLs in memory. And then from there, we can parse the export table of that DLL to resolve imports as needed. And common technique with malware, needed technique with shellcode, and anything else that just wants to try to provide another layer of obfuscation by masking or hiding its API calls until it resolves it on its own. So hiding it from the normal process once an executable is compiled and that import table is built. You have any questions? Drop them in the comment section. Otherwise, look for the next video here that relates to this. We'll talk about resolving dynamic imports.